So I've got a CD here, but it's actually pretty straightforward. Alicia's coming from University of Colorado Boulder, where she just started last year, this year. August, yeah. So very new faculty. She did her bachelor at UC Davis, followed by a master's at PhD. So that's the easy part. Into that. But then she went on to do a postdoc at the University of Birch in Paris, where she was doing shock compression.
No.
Working with someone who does shock compression stuff, who's trying to get you to work on inner core. Okay.
More or less,
then
yeah.
after that, had an NSF postdoc that was split between Swift and Northwestern. And so she does lots of stuff on partial melt, characterizing partial melt, what signatures, what is visible to you from that. And I think that's what we're going to talk to us today, not about concept, but
no.
a little more.
Yes. All right. Well, thank you. I've had just a great day today. I've got to talk about inner core stuff, and I've got to talk about things in the mantle and Yellowstone. So it's been really, really fun for me, and I hope that I can repay the favor and keep you guys a little bit entertained for the next 50 minutes or so, but also get you some interesting science as well. So I'm an experimentalist. It's how I've discovered I define myself is as an experimentalist. I'm really interested in seeing how things work, and in particular, I really, really love liquids, because liquids are weird, and they're gooey, and they're fun, and they're everywhere that anything interesting is happening. So that's really what my research is focused on, and the work that I'm going to be showing you today largely is the culmination of work out of my PhD. I have a tendency to adopt or develop new techniques, so things out of my postdocs and some of my current projects I'll foreshadow at the end of kind of where things are going. But this work is largely what I was working on when I was at Davis. So right here is our, the small blue sphere. Small blue marble, as Carl Sagan put it. So our planet, right, as geologists, we often think about our planet as being, it's built of atoms, and those atoms form minerals, those minerals form rocks, and then we get to a planet. Well, really, when we look at this thing, what defines our planet are the liquid portions, right? Whether you're talking about the ocean, right, that gives us the blue sphere on the outside, or if we're talking about the outer core that gives us our protective magnetic field, or if we were talking about silicate melts in the mantle that are really helping lubricate the planet and giving us plate tectonics and leading to the differentiated planet that we have today. Liquids are really the thing that takes our planet and makes it this unique place that's also great for us to live on top of. So silicate melts in today's story of the Earth, they're a relatively minor component, right? We think about them with volcanoes, maybe at the lithosphere-asthenosphere boundary, but they actually are a pretty big player in a lot of important Earth science questions. So silicate melts and their frozen counterparts, which are glasses, is what we're going to be looking at today. So if you want to understand eruption dynamics, you need to understand how these materials work. Silicate melts are also the most efficient means of moving both heat and mass in planetary interiors. They also, although they might be a small component volumetrically, they play a big role in rheology, being able to very efficiently accommodate shear, and so have a big role in sort of plate tectonics as we understand those processes. And we also often call upon silicate liquids and fluids to account for anomalous regions of geophysical observations like low velocity zones. And in fact, I didn't know this was going to happen, but look, it's Yellowstone. So these two things are really what I'm going to be talking about today, are the role of melt in plate tectonics and understanding the interpretation of low velocity zones. But there's a few other ways where understanding the properties of silicate melts is really important. This kind of is going to foreshadow where we're going at the end, which is with planetary impacts, right? So when we're talking about the moon size or the moon-forming impact in the magma ocean, right? Big dynamics there. Also, if we want to understand the history of meteorites, we need to understand these things. And then there is a direct component to the fact that glass, frozen silicate melts are one of the most valuable, right, sort of technological materials that we have. We use them all the time and we exploit a lot of their really interesting properties. So in the words of Maria von Trapp, let's start at the very beginning. All right, so we were taught, right, that there's 3 phases of matter, right? Solid, gas, and what's our third one? We're going to ignore plasma. Very good. All right, so liquid. There we go. So we're all geologists. It needs to be in a beer mug. So liquids are interesting, right, because they share some of the properties of gases in the fact that they can change their shape, right? They don't have a rigid fixed shape. They can, they're mobile, much like this cat here. However, they have a fixed volume, right? There are some properties where they're similar to a solid. Hopefully this cat doesn't change in volume or something has gone terribly awry. And so because of this, we often, because it kind of, liquids have these similarities to crystals and they have these similarities to gases, we often like to approximate their behavior as either really high density gases or really low density solids. And what I'm going to tell you today is that that doesn't seem to work. When you look at the data, liquids behave differently than both gases and crystalline solids. And so if we use what we actually see in the data, there's a very different physical property and pressure relationship that we would expect that changes our interpretations of seismic velocities. All right, so just a little refresher here. So most of you guys have been through mineralogy at some point in time. So this is our friend crystalline SiO2 quartz. So you can see that its framework is built up of these little silica tetrahedra. And what you'll notice is that in amorphous silica, so this is a snapshot of glass, although a snapshot of liquid would look exactly the same at certain temperature conditions. What you'll notice here, though, is that it's built fundamentally, right, of the exact same building blocks. And in fact, if you were like this little silica tetrahedra here, your life would seem very similar to this little silica tetrahedra here, right? You're connected to other ones on your vertices, but what you notice is that as we move off into space, we lose that periodicity. So silicate liquids and silicate glasses lack long-range ordering, and this is what gives them a really unique way to densify. Just to show you really quickly the relationship between glasses and liquids, because what you're going to tell me is liquids aren't glasses and glasses aren't liquids, and that's kind of true, except for it depends really on how long you look at something. So liquids, right, so here's a plot of volume versus temperature. And so this is what we've all studied, right, where you have a liquid, you cool it down. When you hit the melting temperature or the crystallization temperature, there's a large volume collapse as the atoms rearrange themselves, and then you have a crystalline phase. Well, what happens with a liquid that you cool below the melting temperature is that it continues along the liquid path for some region, and then it becomes a glass. And at that point, you have the atomic structure frozen in of the liquid phase, right? But now you can take it and you can hold it in your hand. So this is a way that as experimentalists, we exploit using glasses to probe the liquid state because they have the same atomic structure as the liquid does at high temperature, but you can easily do experiments on them. So that's why we use them. So let's talk about where silicate liquids are in the Earth's interior really quickly. So we know that there are silicate liquids inside because they come out on the surface, right? And so we can see that with volcanics, right? You can also see that with, we often don't think about this, but actually kimberlitic eruptions, right? Those are silicate melts. They just actually are very high in carbon. So these are some examples here of kimberlite and diamond inclusions. There's also, but really, even the deepest diamonds only measure up to about 400 kilometers or so. Those are the ones that are coming out of Brazil, these ultra deep diamonds that have like the ringwoodite inclusions and those sorts of things. So 400 kilometers is not very deep into the Earth. How do we get farther than that? Well, we use this really cool relationship that was observed by Francis Birch in about the 1960s, 1960, 1961. He had a few papers that came out, and what he observed is that as you increase pressure, you have a corresponding increase in density. And so that's what's shown here in green is as we increase pressure, we have an increase in density. So these are 1D global models. So density, S-wave velocity, and P-wave velocity. And from seismic velocity, before we had experimentally even been able to find or reproduce these phases, what we found were that there were these discontinuities associated with the transition zone. These predicted the fact that we had these crystalline phase transitions, which we later found experimentally. So this has been a really powerful tool in sort of solid crystalline equations of state, being able to actually predict phases before we're able to produce them in the lab. All right, so what I'm going to spend the rest of the time telling you here is that amorphous silicates are really weird. So this is a shout out to UC Davis. We have cows with holes in them. So silicate liquids are really weird. They don't follow the patterns that we expect to see. Yeah, sorry, you can't unsee this. It's with you forever. You're welcome. So amorphous silicates, though, are really, really weird. They actually often don't follow the patterns that we expect to see for physical properties at high pressure based on crystalline relationships. And we're going to start out looking in depth at Birch's law, this really, really powerful tool for crystalline materials. So what Birch's law says is that there is a collinear increase for P-wave velocity with the density. So for constant mean atomic weight. And what constant mean atomic weight is basically the formula weight divided by the number of atoms per formula unit. So most silicates are around 20 to 23. It's just the way aluminum, silica, oxygen, they add up. So these dashed lines are mean atomic weight. Here we have P-wave velocity, we have density. And you can see here that, so we have quartz, albite, anorthite, coesite, forsterite, wadsleyite, ringwoodite, right? And so to a first order, there is a collinear relationship between density and increasing velocity. It's really useful to look here at the polymorphs, so between quartz and coesite, or the Mg2SiO4 polymorphs, and you can see that, again, to a first order here, they lie on this line of constant mean atomic weight, where you can predict the P-wave velocity if you know the density of a material. All right. This also holds if you compress a single phase under pressure, so that's what's shown here. So we have a single phase, and we increase the density by just exerting pressure, reducing the volume. And you can see again here for instatite that you have the same sort of first order positive linear correlation between density and P-wave velocity, even as you go through a phase transition. All right, let's look at silicate melts. Well, here they are. So I've drawn lines here to correlate. So this is SiO2, that's phthalate there. And what you're going to notice here is that regardless of density, we have a very narrow range of P-wave velocity for these crystals, or for these melts. The other thing to notice is that the relationship between the density of the melt and the density of these crystals, right, unlike what we saw before for quartz and coesite, where they have this collinearity, you see that it breaks here when we start looking at silicate melts. Here's some data for silicate glasses. You can see that here you have a higher P-wave velocity because the temperature is lower. They're a solid phase, but again, there's this relatively narrow P-wave velocity band for regardless of what the densities are for these materials. If we look at, things start to get really interesting though when we start to look at the relationship between density and P-wave velocity for silicate glasses at high pressure. All right, so this is the same basic plot. Again, we have density at the bottom and P-wave velocity along the side. Here are our, these dashed lines, right, our crystalline silicates. Here's our band for the relationship between P-wave velocity and density for our silicate melts. And what you'll notice up here we've got a wide range of compositions, everything from instatite, basalt, SiO2, albite, jadeite, right? These relationships are very different. As you compress these materials, sometimes the velocities decrease as you increase pressure, right? That's not what's supposed to happen with Birch's law. In other cases, there seems to be this near density or pressure independence for the orthopyric or the pyroxene glasses. So this is a very different behavior, much more similar to what we see here, where we can change density without having a corresponding increase in velocity for silicate glasses at high pressure. There's also a bunch of other ways that silicate liquids are weird. One of the things is that normally, right, as you heat up a material, this is for SiO2 here, but as you heat up a material, you expect that the density is going to decrease, right, which is what we see here. However, once you get into the supercooled liquid, so this is the temperature range where it's technically a liquid, but it's below the crystallization temperature, the density of SiO2 actually increases as you increase temperature. And the reason for this is that there is two coexisting phases. So in this case, we have polymorphism. So there's two coexisting liquid phases in SiO2 melt at 1 atmosphere. The other thing is that we've known for almost a century now, this work was done by Bridgman in 1939 on silica glass, but in about 2013, we saw the same thing in basalt. And what these two plots show is that there's a region of increasing compressibility or rapid densification for silicate melts that you don't see in crystalline materials. So traditional crystalline equations of state, right, as you increase pressure, it becomes harder and harder and harder to reduce the volume. And so each incremental density increase decreases as pressure goes up. What you see here for both of these is that you actually have this region where it becomes easier. The material becomes more compressible as you compress it. All right, let's look at electrical conductivity. Let's just keep going here. So for electrical conductivity, as pressure increases in crystalline materials, so this is for the Mg2SiO4 polymorphs shown here, as pressure increases, or depth in this case, the conductivity, so the ease with which atoms can hop through the lattice actually increases. And this is because you're basically shrinking the hopping space, right? You're moving everything closer together, and so it becomes easier for atoms to hop from one site to another. So conductivity increases as the lattice comes closer together or pressure increases. However, we see the exact opposite behavior in silicate melts. So this is for an andesitic melt up to about 3 GPa. But what you can see here, right, is that as we increase pressure, we actually have a decrease in the electrical conductivity. It becomes harder for atoms to move around. All right, what about the effects of volatiles? So volatiles in silicate crystals decrease their bulk modulus. So the volatiles are incorporated into the atomic structure. Here's an example for wadsleyite. No, ringwoodite. So here's an example, and you can see that here we have a little magnesium atom, that's the blue guy, and it's been replaced by a hydroxyl unit that now has to be charge balanced by a vacancy. A hydroxyl unit is a larger physical volume than a magnesium atom. So you're expanding out the structure and you're putting more holes in it. So you're making it softer, you're making it squishier. And so there's been work done that shows that the bulk modulus or the velocities, either which that you would like, as you increase the water content, the velocities decrease. That makes sense, right? It's getting softer, it's getting squishier. Well, glasses and melts can incorporate volatiles in two ways that aren't available to crystalline silicates. So one of the first ways is shown here, which is that they can bond directly to the silicon atoms, so they actually don't necessarily depolymerize the melt when they're incorporated in. The other thing is that they can sit in these big interstitial void spaces, right in there. And what that does is it actually reduces the amount of volume that can be compressed. So this is some work that shows this. So this plot here is pressure versus strain. You can think about it as volume if you want. So density is increasing this way. This is for SiO2. And what you see, so this is the bulk material, right? As you compress it, the volume goes down, the density is increasing. If neon or helium is around, what happens is that you actually have a much stiffer response on compression. And that's because you can absorb volatile species into these interstitial void spaces like there. We also see that there's a very different response for P-wave velocity. So this is some work showing the difference between P-wave velocity with noble gases around for helium and neon versus sort of the intrinsic material properties. And you can see that there's a much stiffer response when there's volatiles around. And actually, there was just some work done that shows that water does the same thing. And we're done. All right, so this is the emoji of scientific inquiry. So this gets to the question like, okay, at this point in time, I've given you, what, 6, 7 different physical properties that don't behave how they should if crystals can, or if silicate liquids can be modeled using crystalline equations of state. What's going on here? Why are these things behaving so differently? And the reason is because they can densify by different mechanisms, right? For crystalline silicates, you have bond compression, right? Our idea that we learned in physics or chemistry, right? Where your atoms are connected by springs. As you compress those, you reduce its volume, but it becomes harder and harder to reduce the volume as these springs get compressed. However, amorphous silicates, right? We have this lack of long-range order. So you actually gain some degrees of freedom or atomic sort of mobility. And I like to use this toy to try and explain this idea. So we've all played with these, right? So we can reduce the volume of this Hoberman sphere by the rigid rotation of these plastic pieces relative to each other. Oh, lol, you've been playing with it. Okay. So, right? So you can see that, right? So we're not actually deforming any of these plastic pieces. We're just rotating them relative to each other, right, to get this volume reduction. So this is a very low energy mode of densification. You can imagine seismic velocities are not going to increase if we can densify this way rather than having to densify by compressing the springs and making the material stiffer. So now that I've kind of given you the background, I'm going to walk you through some of the data that I've collected. And first I'm going to show you a couple techniques, just really briefly. I use a wide range of experimental techniques because I think it's fun, mainly, but also because I think that trying to probe questions in a lot of different ways can give you some interesting answers. So combined, I've used, like Lowell says, electrical conductivity, density, atomic structure, elastic properties, and I'm starting to get into sort of a shock compression regime as well now. So a lot of my, one of the things that I need to do, right, for these experiments, I've told you that velocity and density don't seem to be as well coupled in amorphous silicates as they are in crystalline silicates. So I need to measure density separate from velocity. Most of the time, if you look in the literature, one is measured or the other, and then you basically just use thermodynamic equations to calculate either velocity or density from whatever you happen to be measuring. So to measure density of amorphous silicates is difficult because they don't have any long-range order, right? So you can't use X-ray diffraction or other techniques that are standard for crystalline materials. So what we do is microtomography. And so these are a bunch of synchrotrons that I've used, but you have a lot of people here that use synchrotrons. They're really high energy X-rays, so we can actually see inside of experiments that are at high pressure. This is the apparatus I use at Jesse Carr's, which is in Chicago. It's a Drickemer-style press. It's about the size of one of Sarah's piston cylinder machines. It's not particularly big, but what's cool about this is that you have 2 anvils, top and bottom, with a gasket, and you put your sample in between. The entire thing is contained in a plastic or alumina, which is also X-ray transparent aluminum containment ring, and then it's put here in between these 2 motors. Now these harmonic drives can actually rotate the sample while it's under pressure. This is a really, really unique capability. And it's also really critical because unlike a CT scan at the doctor where you lay still and the X-ray source moves around, remember how big these X-ray sources are, right? Those aren't moving. So we need to move our sample while it's under pressure. And so this is the way that we do it. So we rotate our sample, we collect a series of radiographs. Once we have that, we have the angular information and we can reconstruct a 3-dimensional rendered volume. If we do this from 1 atmosphere to high pressure, we can then reconstruct a compression curve and we get density. All right, to measure velocity, I use ultrasonic methods using the diamond anvil cell. So this is gigahertz frequency interferometry. It's a pretty simple system. You have a transducer on the back of a buffer rod. And what happens is that at every interface, right, some of the wave is transmitted and some of the wave is reflected. And what we do is we basically just look for the reflected wave from the near and the far side of the sample, right? And that tells us how long the round trip travel time was in the sample. And if we know our sample length, we can calculate velocity. We do this in the diamond anvil cell, and we use, to constrain length, we use our density that we measured independently using tomography. Just a couple cool things about gigahertz interferometry is that because it's an acoustic wave rather than using lasers and inelastic scattering, you can measure very interesting materials like opaque materials like FeO, which Mike and I were talking about earlier. It's also very well suited for glasses and liquids, which is a lot of the work that I've done. And it can also be used for super hard materials. So we've started working on trying to measure the elastic properties of diamond, which shockingly has never been done before. So these are little diamond discs that I was cutting out of a diamond plate at APS with a laser, and the laser had a letter function. So of course I wrote my name in diamond with a laser, because wouldn't you all if you had that opportunity? All right, so let's go back and talk about silicate melts in the Earth today. So we know that there are silicate melts in the Earth today, and one of the big ways that we know it is because there are places in the Earth where seismic wave speeds are slower than we would expect them to be based on a 1D global average model. All right. One of those regions is the lithosphere-asthenosphere boundary, right? So we have this global feature where there is a sharp discontinuity at somewhere between 60 to 100 kilometers, maybe a little bit more depending on your exact region. And this is often in the literature been attributed to the presence of silicate melts. So we're going to focus on applying my results to the southwestern Pacific. So there's been a couple studies in this region for both P and S wave velocities that have reported about an 8% velocity reduction at depths corresponding to the lithosphere-asthenosphere boundary. Okay. But if we want to try and interpret seismic velocity reductions, we need to know a few things. We need to know how melt affects seismic velocities as a function of pressure, right? The depth at which we see these anomalies. The volume of melt that's there is going to affect the magnitude of the seismic velocity reduction. And then the last thing is that the geometry of the melt phase is going to also have an effect on how large of a velocity reduction we would expect to see. All right, so let's go back here to our data for silicate melts and silicate glasses. So we're going to create an empirical equation of state, because I'm an experimentalist and I can collect data, but I'm not very good at developing new equations of state. That's for somebody else to do maybe. But what I can say is that for silicate melts at the lithosphere-asthenosphere boundary, we would expect, right, when we're melting the upper mantle, we expect basalt composition, right? So we see that there's this weak pressure dependence for basalt so what we're going to do is we're going to take this weak pressure dependence and then we're going to apply it to silicate velocities, right? So we're just taking the pressure dependence and applying it to the 1 atmosphere basalt acoustic velocity, and that's what I've shown here. So this is the Earth, so you have depth or pressure, however you would like it, with the different sort of regions of the Earth. We have P wave velocity, and then this black line on the far side, that's our 1D global average model, right? Velocity is increasing as depth is increasing. The gray band here is how previously melt velocity has been modeled. You're going to notice here that it's subparallel to what we see for the crystalline materials, and that's not surprising because we've just taken the 1 atmosphere velocities for melts and we've applied crystalline equations of state, and that's what we're going to predict. However, what we're saying is that there's going to be this very weak pressure dependence or density dependence for silicate melts, at least up to about 3.5 grams per cc for basalt. We have data that shows that basalt doesn't go under any sort of phase changes or coordination changes or anything like that at these sorts of pressures. So we're going to say, okay, at this point in time, it's just going to densify by this sort of very low energy density mechanism. And so for that, we're not going to see really very much of an increase in velocity. And you can see here at the transition zone, we would expect nearly a factor of 2 slower velocities. And there's a 20% velocity reduction at the lithosphere-asthenosphere boundary. So these aren't particularly small or insignificant differences in melt velocity for some of the regions that we expect to see silicate melts produced. One of the things, though, that I told you is that not only do we have melt fraction, so now we know that we have a good equation of state for melt. We know about the depth that we want to go to because it's the lithosphere-asthenosphere boundary, but what about melt geometry? Well, so for that, I'm using this analytical solution from Takei. Her work is based both on some analytical solutions and also some work on analogs that she's done. And the important thing here is not most of the things, but basically that the velocity reduction, so the decrease from what we would expect, right? So this is the percent velocity reduction from sort of the 1D global average model is dependent on a geometric factor. That's what's shown there, or these guys here in blue. Melt fraction, shown in red. And then for P-wave velocity, also this factor beta, which is the ratio of the bulk modulus of the solid to the liquid. So for those of you who don't think about this all the time, right, the bulk modulus is the response to reduction in sort of volume, sort of an isotropic compression, and it is dependent on velocity and density. And so for our seismologists in the room, this is the equation you would recognize. It's that one over there. Okay. So one of the things that you'll notice here is both of these equations, right, are dependent on this factor of the melt fraction over 2. If we're looking in the same area, the melt fraction should be the same. So if we take the ratio of the S to P wave velocity reduction, we can basically constrain the geometric factor, which is why it's so important to have both P and S wave velocity reductions. So to get into our model, right, we needed this beta factor, which is the ratio of the solid to the liquid bulk modulus. And just to show you here the difference, again, so here we have the bulk modulus of our global average Earth in the dotted line. Here's the traditional equation of state where you can see it's subparallel again. And here is our, what we call the network flexity densification model. And you can see, again, there's a very weak pressure dependence for this. So we don't have to worry about what's happening with our shear waves, right, in this particular case, because in the liquid they're not sustained. So it's just this P wave velocity reduction. This is the only experimental factor really that we needed to constrain to solve these equations. So we're going to look at some different geometries. So for our study, we looked at everything from isolated melt pockets to melt films or bands. In the Earth, we really only expect equilibrium melt textures, so kind of pooling, ponding melt in a crystalline matrix, or melt films and bands in regions like the lithosphere-asthenosphere boundary. So let's look at our data now. So here's our S-wave velocity reductions calculated as a function of pressure for different melt fractions. So we're going from 1%, 3%, 5%. And the data that I'm showing here is for the equilibrium melt texture, although it would hold for any other geometry for the general trends. The magnitude would change, though. So not surprising, if we use either model, we get the same value here for our S-wave velocity reductions. Now let's look at P-wave. So this is for sort of our traditional crystalline equation of state. And what you can see here is that there's a very different trend expected between the P-wave velocity as a function of pressure, right? So what you can see here is that there is a decrease in the effect of a constant melt fraction with increasing pressure. However, what we see for the network flexibility model is that there's actually relatively constant velocity reductions, and they're also relatively similar in magnitude for a given melt fraction, right? So here, our 5% melt fraction are relatively close. You know, it's about 9% for 9 to 10% velocity reduction over the entire upper mantle, whereas here we can actually start to get quite a large difference between our predicted P and S wave velocity reductions. All right, so let's look at melt fraction now, or in a minute, whichever. So what we have here are our different melt geometries. So this is the ratio of the S to P wave velocity reduction. So this is independent of melt fraction. So we again have pressure on the bottom. Here's this ratio on the top. And so we have our three different models, our interconnected sort of sheared melt, our equilibrium pooling melt, and then very similar down here is isolated melt pockets. So this is using our model. You can see that, again, there's this very weak pressure or density dependence, whereas sort of the way that these things have traditionally been modeled is that there's a very strong dependence on density and thus pressure for the VS to VP ratio. So let's apply this somewhere now. Let's think back to the South Pacific. I told you at the beginning that there's been quite a few studies that are reporting about an 8% velocity reduction for both P and S wave velocities. So if we take the ratio of about 8 to about 8, we end up at about 1, right? So this means that we can pretty easily explain these velocity reductions by having melt in equilibrium geometry, so pooling melt, not sheared melt, using our model. And one thing that's really great about this is that, again, if we have about an 8% velocity reduction, that's about 4% melt that's predicted in these areas. And this is consistent with volcanic observations in the region where there's these petite spot volcanism. So you have to have enough melt that's pooled that it can actually come to the surface. So you're having some small percent, 4 or maybe greater. But to a first order, this seems to be consistent with what we're actually seeing in the region. One of the things that you're going to notice, right, we're talking about the LAB. What is it not? It is not sheared melt, large planes of melt in this aligned fabric. That's sort of this channelized melt idea that we've been talking about sort of that would lead to free-floating plates, free-floating lithospheric plates. So our data seems to suggest that there's no strong fabric in the melt phase, which would mean that there's, at least on these older plates, that there's stronger coupling across the LAB than has been previously assumed, which would have implications for larger scale planetary dynamics. All right, so on the last few minutes that I have here, I'm going to talk to you a little bit about what I have been up to since working on this study. One of the things that I did, as Lowell was talking about, was during my postdoc that I spent at Scripps and at Northwestern, I started to try and expand the pressure, temperature range, and also the compositional range to start looking at partially hydrated silicate melts, right? So unless you're talking about a plume or maybe a mid-ocean spreading ridge, most places you need to have volatiles in order to induce melting, right? Especially when you're talking about seismic or electrical anomalies that are associated with the top or bottom of the transition zone. So we've been pushing the PT conditions that we can make these sorts of measurements. A lot of that work is still ongoing. Also, to complement this, I've started doing these experiments at Sandia National Lab on this machine called Thor, which has a pretty great name, although somebody pointed out that we missed the opportunity to have it named Predator. But so this is about the size of a person. So this machine uses electrical energy. It's stored back here in capacitors. And then the electrical energy up to, I think it's, 2 mega amps, I think is what is released at one point in time. So it's 2 mega amps. So you release all this energy from there's 96 different little capacitors that store, that's what the brick tower is. And it gets released down these cables. There's, I think, 8 miles of cable wrapped around this machine. And then it goes into this central power flow section where it gets dumped into the central section. This here is where the sample is. It's this little thing in here. And this thing exploits the relationship between electrical and magnetic energy. So it basically comes up and around this U shape. So the power would flow up the back side of this and then come around into the front where it would short. you have a lot of electrical current that's going through here. When it shorts out, it produces a giant magnetic field, and that magnetic field, since it's in a U-loop, it's basically doing that thing that we've all done with magnets where you flip them so that the positive or the negative ends are back to back and they press against each other. So that's actually generating all of our pressure. And what's really cool about this technique is, unlike traditional shock where you follow a Hugonio, so you're not following, you're increasing pressure and temperature together very rapidly, you can actually shape the way that the energy goes into the sample, so you can follow an isentrope, and this is what the Earth's geotherm is. So you can actually follow the path of pressure and temperature into the Earth. And just to show you what one of these experiments look like, because it's really fun. And what's absolutely crazy about this to me is, in this experiment, we just collected literally all the data from 1 atmosphere to 30 GPa for this composition. So this is a really, really cool machine that's able to explore a very wide PT range very, very quickly. You enjoyed that, I can see it. All right, let me show you one more. Okay, so here's another shot of Thor. These here are these like crosshatch lines. So this is like that safety glass, right? Watch this. When this thing goes off, you can actually see the pressure wave vibrate the window glass. We have to wait for a second. It's thinking about it. It's very fun. This is the little machine. So we've just started working on this and collecting the data this year. So my graduate student, Lindsay Harrison, has been, she was a champ. She went to her first conference before she even started grad school, and I was supposed to be there and then got caught up in moving things and abandoned her. And she did a great job. But she's looking at the effect of hydration on seismic velocities, basically from 1 atmosphere up through the transition zone, to try and constrain these things. This is some of our very initial data is this red line. And what you're going to notice here is it doesn't do what was expected of it, right? So again, these materials are behaving very strangely in comparison to sort of, so this is density as calculated, which is a problem, from ultrasonic velocities measured by Brion spectroscopy. Okay, and so this work that Lindsay's doing is part of a bigger project that I'm doing at Sandia, which is the big direction that my research program is headed in right now, which is what is the origin of Earth's water? Or basically, how is water or all other volatile species retained in planetary interiors when you have giant impacts like this where you've melted the entire planet? So everywhere we look, there seems to be water, right? This is a big thing that's been very popular in sort of the news media for the last probably 5 years, right? Oceans of water in the Earth's interior. Some of you guys know Brandon Schmatt or Steve Jacobson, or have heard about like the water that's been found in either minerals or possibly even as free fluid as diamond inclusion. So they think that they found ice inside of a deep diamond inclusion. So everywhere we look in the Earth, there seems to be water. And we know that there's a lot of water in the solar system. You know, we recently went to this comet 67P. It's releasing 1.2 liters of water a second into space. So there are some problems with having this much water around and sort of our idea of how Earth got its water. So the canonical view, right, is that you have this giant moon-forming impact. You melt everything, you devolatilize everything, right, based on our intuition from living on the Earth's surface, right? When you heat something up, the volatiles go away. And so later, the water was deposited by comets and that sort of thing, eventually leading to enough for us to have our oceans. Well, so one of the problems with this is that the ratio of the Earth's oceans is actually, the ratio of deuterium to hydrogen, so the light to heavy element, is actually closer to that of the bulk building blocks of the Earth, carbonaceous chondrites, than it is to actual comets. And the other thing is that when we start looking at into sources of deep-seated volcanism, like the Baffin Islands off of Iceland, again, the deuterium to hydrogen ratio is actually seems to have this primordial signature. So this here shows the DDH ratio. So this is the protosolar nebula, so our gas giants are hanging out down here. Our comets are up here, but you can see the bulk Earth is here, and like the Baffin Islands is down here. So there seems like we've retained some of our primordial water from planetary formation, and how can we do this? Well, the idea is, well, silicate melts generated at high pressure might have a way of storing volatiles inside of them, right? You could fit a volatile in this, and if it's under high pressure, you might be able to just keep that trapped in there until it solidifies, right? So we want to be able to understand what is the equation of state and how do volatiles affect the physical properties of magmas at very high pressure. This is much higher pressure than we've been talking about. You know, most of my work up till now has been in the upper mantle, and now we're going basically to the core mantle boundary pressure, or even higher when we're talking about the actual impact event. And so that we're doing on the Z machine at Sandia National Lab. This is a really, really cool machine. You should Google it. There's some fun videos on it, but it's 33 meters in diameter. This is one machine. It does one experiment a day. There is this interior part in here gets filled with water and oil as insulators, and the shock wave that is generated during an experiment is so big that there's a scuba diver employed to scrub bubbles off of things so that they don't cavitate when the shock wave goes through and damage the equipment. Each shot takes 95 people to run. It's also the weirdest type of experiment that I've ever done because I'm not allowed to touch anything. It's very strange. So just to kind of go back to what I was talking about a little bit earlier. So this is a shot of the Z machine in action. This is the one. And so one shot from the Z machine carries more than 1,000 times the electricity of a lightning bolt, and it is delivered 20,000 times faster. So they can generate the conditions inside of stars, definitely inside of planets. And one of the things that you'll notice here is that all of this really fun stuff, all the arcs, they're coming off of this 3-point interface between the metal ladders, the water, and the air. And so the interfaces and the liquid phases are really where we're getting a lot of this interesting sort of behavior, which is why I really like working on these things. So with that, that's everything. I have been supported by a lot of people and a lot of various foundations and facilities, so I just wanted to do that really quickly. So with that, thank you so much for your attention.